and the important process that we are talking about, ECM, and we are talking about material removal rate of that ECM process. Is it okay, everybody? Please write in the comment box so that we'll start the session. Let the students join, and today we are going to discuss the important formulas, as well as we are going to discuss some formulas or numericals question which were asked in a previous GATE examination. So let's join everybody. Right, fine. Okay, everyone. Fine. So shall we go back and discuss and recap what exactly we have discussed in the previous session? Okay, fine. So let's say that we were talking about a non-traditional process which is called as ECM, that is called as electrochemical machining operation. So now whenever we talk about electrochemical machining operation, we have discussed that the mechanism of removal of material of electrochemical machining operation is nothing but ion dissolution or ion deplating. Now whenever two conducting metal electrodes are immersed in a conducting electrolytic solution, whichever electrode is connected to the positively charged terminal, it will start depleting the ions. And whenever the ions are depleting, that is the majority of the portion of material removal principle. Now, what are the influencing factors of MRR? So it was discussed that the MRR is directly proportional to amount of charge carried per second. And when we talk about amount of charge carried per second, which is nothing but a current. And simultaneously, MRR is also directly proportional to electrochemical equivalent. And electrochemical equivalent is exactly equal to gram atomic weight divided by valency. So therefore, we have discussed that we have just particularly convert that into one mathematical model, and we have just got one formula, right? Fine. So what was that formula? So we have discussed that mass material removal rate is exactly equal to A into I divided by Z into F. A into I divided by what? Z into F. And the unit of this is exactly equal to gram per second. Gram per second. Is it okay, everyone? Write down in the comment section how exactly it is. I hope so. Everybody's understanding. Yes. Good evening, Jeevan, Vishnu. Yes, fine. So we are going to solve a numerical now. Now, whenever question is coming, there might be chances that it can directly mention that calculate mass material removal rate, or sometimes there might be chances that calculate volumetric MRR. So for calculation of volumetric MRR, we discussed that mass material removal rate divided by density is exactly equal to volumetric MRR. Is it okay? Yes. So till now we have discussed. I hope so you are understanding this. So rho is exactly equal to density plus, please understand that whatever the density value is, that should be written or mentioned in terms of what? Mm cube per second. Or sorry, density has to be in gram per mm cube, right? Fine. And if I put the density in gram per mm cube, my answer will come, that is volumetric MRR. It is mm cube per second. Mm cube per what? Second. Is it okay, everyone? Yes. Now, we had discussed yesterday that there might be chances that the question might come for pure metal or question might come for alloys. So, pure metal or alloys. So, if I talk about pure metal is nothing but, suppose if I taking example that pure copper, right? Fine. A copper material. So, if I select a copper material, can I say that, sir, for copper material, it's a pure material, then can I say that it has only one valency Z? It has only one gram atomic weight, right? There is no question of anything. And it has valency, it has gram atomic weight, and it has a unique density also. Is there any problem? No. If there is a pure metal, then for that metal, valency would be constant, gram atomic weight would be constant, and density will be constant. So if these things are there, so therefore where I am asking you to calculate mass MRR or volumetric MRR, we can definitely going to get and calculate this. So mass material removal rate or mass material removal rate is exactly equal to what? A into I divided by Z into F. So gram atomic weight is given, the current is given, valence is given, Faraday's constant we know that we can calculate, and the answer will come gram per second. because the values are constant, there is no dilemma. In the same manner, I can calculate a volumetric MRR. I can calculate what? A volumetric material removal rate. What is volumetric MRR? Sir, we know that mass material removal rate divided by density. Density से क्या करना है? Divide करना है. Is it true? Yes. So we can say that it is exactly equal to A into I divided by rho, that is density, into Z into F, and now answer will come exactly equal to what? It will come mm cube per second. Mm cube what? Per second. Till now I don't have any problem. Is it true? Okay, what is Vishnu? What Vishnu is saying? Mass removal rate divided by density. Very correct, Vishnu. Right, fine. Good evening, everybody. Now we are talking about alloy material and discuss about the different dynamics of this particular process. So what exactly is alloy? Alloy is a combination of different material. Suppose there is a alloy of copper and the aluminum. So I am selecting aluminum, I am selecting copper, and I am mixing together. So in certain percentage they are going to mix. So suppose I am mixing two material, definitely there must have been certain percentage in which they are going to mix. Suppose let's take an example that there is A material and there is B material I am mixing, and then by mixing I am just manufacturing a alloy, and that alloy is nothing but called as AB alloy, right? Aluminum, copper, whatever it may be. Now if A and the B material is different, can I say that material A will be having its own density, own valency, and own gram atomic weight, and same thing is applicable to B material also. So B material will be also having its own density, own weight or gram atomic weight, and own valency, and same thing is applicable to copper and aluminum. If copper and aluminum are mixed together, copper is having its own density, gram atomic weight, and the valency. Same thing is applicable to aluminum. Is it true? Yes. So we can easily write down here in a simple manner. I'll say that A material and B material are two different material. They are having their own values of density. I'll say that rho 1. It will be having their own valency Z1. It will be having their own gram atomic weight. Let's say that A1. Same thing is applicable to B also. Rho 2, Z2 and A2. For example, I am talking about. For example, I am taking a hypothetical example here. Now, if A and the B are material mixed together, and now the valency of A, density of A material, and the gram atomic weight of A and same value of B are given, and then the question is coming, calculate mass material removal rate or volumetric material removal rate. Now the question would be coming, sir, okay, all the values are given here, but whenever I have written the formula here, it is A into I divided by rho into Z into F. So we have to put gram atomic weight, then we have to put a density value, and we have to put this valency value. Now the question is whether you will be selecting value of this of A material, or whether you are selecting value of this B material, or whether you are taking an average of it. This is the biggest question is coming, and that's what exactly dilemma. So it's very simple that suppose if in the alloy it is assumed that A material is of 90% and B material is of 10%. Hypothetical example, let's select. What I'm talking about, suppose A is 90%. What is that? In alloy, A is 90% and B is 10%. Right, fine. And then while calculation of that volumetric MRR or mass material removal rate, students are saying that we should take average. That is density of A material plus density of B material divided by 2. So that value we should select and calculate mass material removal rate. It is absolutely wrong. Is it accepted, everyone? Jeevan, Vishnu and rest of the students? It's very true. So can I say that if in that alloy A material is 90%, which means that the material removal rate up to a 90% is controlled by A material, because A is 90% and B is merely 10%. So MRR will be influenced more by A and not by B, because B is only 10%. So therefore, whenever the question comes for alloy material, you have no right to use a value of A or B, but you have to select a weighted average. And the weighted average stands for, we have to give a weight. A is 90%, so 90% weightage should be given to the density of A, valency of A, and gram atomic weight of A. If the B is 10%, then relevant weight has to be given. So you must have heard and understood that. What is it? What exactly we have to calculate? We have to calculate weighted average. We have to calculate weighted average. Now how to calculate weighted average here? Let's take an example. What is that? Suppose I'll take one example here. Mass material removal rate I'm talking about. Mass MRR. So what is the formula for mass MRR? Sir, it's very simple. A into I divided by Z into F. So I'll say A into I divided by Z into F. Z into what? F. Right, fine. Now you do one thing, that whatever this gram atomic weight is there, okay, that gram atomic weight, you just take it to the denominator. Don't put it in the numerator. So I'll say that, sir, mass MRR will come here like what? Mass material remole rate will be exactly equal to I divided by what? Z divided by A into F. Do you understand, everyone? Yes. And now we have to select what? We have to select a weighted average. So I'll say that mass material remole rate, how exactly it can be? Mass material remole rate is exactly equal to. Now let's take a hypothetical example that we are talking about. Now we have selected here the material A is 90% and B is 10%. Now these are number, for example, we have selected. Suppose if I select that material A is X percent. For example, X can be anything. It can be 10, 20, 30, 50 or 60 or anything. So if in the alloy AB, if A is X percent, how much will be a B? If A is X percent, sir, B will be definitely 100 minus X. Is it accepted, everyone? It will be what? 100 minus X. Is it correct? Fighter, just 2 minutes. We are going to solve a numerical here. And we are going to fight. Vishnu, everyone, we are going to solve the numericals. Don't worry about it. So I'll say that, sir, if A is X percent, so B will be definitely 100 minus X. So therefore, how exactly this weighted average can be written? Let's say that, sir, it is exactly equal to I, right? It is exactly equal to I divided by Z1 divided by A1. And how much it is? It is X percentage, that is X divided by 100. X divided by 100 plus what? Plus, can I say that? Z2 divided by Z2 divided by A2 into 100 minus X divided by 100 divided by 100. This is weighted average multiply by Faraday's constant F. So this is the formula we have to use. Mass material remole rate is exactly equal to I. That I stands for current, F stands for Faraday's constant, and then for A material, whatever valence is given and whatever gram atomic weight is given, you put it there along with its percentage X. And it should not be 1000. Okay, fine, very correct. It's not should be 1000. It should be 100, right? It should be what? 100. It should be 100, not 1000, 100. Is it okay, everybody? Yes. Now the next question is coming. Let's say that, sir, instead of mass material remole rate for alloy, if question comes calculate volumetric MRR, then density would be also coming in the picture. If the density is also coming in the picture, you go back and look into the formula. What is the formula? So volumetric MRR, you can easily understand here. What is volumetric MRR? A into I divided by rho density into Z into F. So A, if I take to the denominator, so there will be density multiplied by valency divided by A. So this simple formula can be written like this. I hope so you are understanding this. I'll say that, sir, volumetric MRR, volumetric material remole rate. In the same manner, I'll do one thing, that current I'll keep it at the numerator. Current will be there at numerator divided by, can I say that it will be exactly equal to F, that will be constant. Here I'll say that Z1 into rho 1 divided by gram atomic weight A1 into X by 100 plus, I'll write down here, plus Z2 into rho 2 divided by A2 multiply by 100 minus X divided by 100. Is it true? Yes. This is a complete bracket. This is what exactly a complete bracket would be there. Is it true? Yes. So this is what exactly. So if density is also given for volumetric MRR to be calculated, so density also individually uses to calculate it. As simple as that. Okay. So volumetric MRR we can calculate. Mass material remole rate also we can calculate. Is it true? Yes. Now again one more question is coming. Instead of giving the density separately, right, density of material A and density of material B, there might be chances alloy density might be given in the problem, and it can be considered as AAB or rho AB. This is called as density of alloy. Understand this point very correctly. Without that you can't able to solve numerical. Density of alloy. So how exactly density of alloy? Instead of giving density of A or density of B, density of alloy is given. If the density of alloy is given directly, so it's very simple that whatever the value of that rho 1 and the rho 2, you take it into that particular bracket, you take it common directly, and directly you put it value of rho density of alloy. That is rho AB, density of alloy. You don't require to multiply individually rho 1 and rho 2. So therefore, my new formula would be coming, that is exactly equal to volumetric MRR, volumetric material removal rate. How exactly volumetric material removal rate? Current will be as it is stagnant, standard, and then I can say that divided by what? I'll say F, Faraday's constant. I'll say rho, that is density of alloy, into what? I'll say that, sir, valency and the density. What is that? Valency Z1 divided by A1. So I'll say valency Z1 divided by A1 into x by 100 plus Z2 divided by A2, Z2 divided by A2 into 100 minus x divided by 100. Do you understand that? Do you understand this particular, everyone? Right? So this is the way by which the volumetric MRR can be calculated. This is the way by which what? Volumetric MRR can be calculated. I hope so you are understanding. Write down in the comment box, everybody, so that we can understand. Fine. So we can do one thing, that now we can go and try to solve certain numericals, right? Simple numericals we can start solving, right? Fine. So we can say that you write down here answer to this particular question. The primary mechanism, so you tell me that, what is that? The primary mechanism of material removal in electrochemical machining is it the chemical corrosion, or etching process, or ionic dissolution, or spark erosion? What is it? So we can say that, sir, it's very simple, that primary mechanism of material removal is nothing but exactly equal to ionic dissolution, because ions are depleting, and when the ions are depleting, material removal takes place. So my answer to this question is exactly equal to ionic dissolution. What is the answer? Ionic dissolution is the answer. Is it true? Yes, ionic dissolution. C is perfect answer for this particular question. And can you believe that this particular question was also asked in a GATE examination? It is also sometimes called as a ion depleting. It is also called as what? Ion depleting, ion depleting, or ion dissolution, or ion depleting. Is it true? Yes, Vishnu, very correct. We'll go to the next question now. Right? Fine. This is not the question, very simple question, we'll take it, and then we can be able to understand that. Right? Fine. So this is the question. Everybody can try and understand and solve this question. So the question statement is that in an electrochemical machining operation, a square hole of dimensions 5 mm by 5 mm is drilled in a block of copper. The current used is 5000 ampere, atomic weight of the copper is 63, and the valency of dissolution is 1. The Faraday's constant is 96,500 coulomb. The material removal rate is. Please calculate and comment. Write down in the comment box what exactly answer would be. Write down the data which is given there. Everyone, Vishnu, and then G1, and then Fighterman. Everyone, please write down this particular in a comment box. So what is it? Electrochemical machining operation ka material removal rate we have to calculate. And the formula also we know that. What is the formula? The formula is very simple, which is nothing but A into I divided by Z into F. Right? Fine. So we can say that it's a very simple story. Sir, material removal rate is exactly equal to A into I. A into what? I divided by Z into F. So what the values are given, I'll write down here. Sir, it is given that the current use, that is I, exactly equal to 5000 ampere. 5000 ampere is a current given, right? The gram atomic weight, so I'll say that, sorry, not density, gram atomic weight. So we can say that A, gram atomic weight is given. So I'll say that gram atomic weight A is given. It is exactly equal to 63. Gram atomic weight is given what? 63. Okay, fine. 3.26, absolutely correct. Then the valency Z is exactly equal to 1 and the Faraday's constant F is exactly equal to 96,500 coulomb charge. 96,500 coulomb charge. So when entire data is given, you have to put that value into the formula. And we know that these all the values are given in the standard unit. You don't require to take, because gram atomic weight has to be in gram, not worry, right? Fine. So we can put the value in a standard form. So what I can write down? Material removal rate is exactly equal to A into I divided by A into I divided by Z into F. So I can say that material removal rate is exactly equal to A. A stands for gram atomic weight. So how much is gram atomic weight? 63 gram. Multiply by current. How much it is? 1000 ampere is exactly equal to current it is flowing. Or how much it is? I think so it is 5000 ampere. 5000 ampere. So we can say that and replace it here easily. So we can say that 5000 ampere is a current. Okay, 5000 ampere. Valency Z is exactly equal to how much? 1 and Faraday's constant 96,500 because it was directly given. If agar nahi diya hai, it can put that 96,540 coulomb charge, right? Fine. And then if you calculate this, material removal rate is coming exactly equal to 3.26 gram per second. 3.26 gram per second. So this would be my final answer coming. Material removal rate is exactly equal to 3.26 gram per second. Is it accepted? 3.26 gram per second? Yes, 3.26 gram per second is the answer is coming. And you can easily understand here, it was not mentioned that whether to calculate a mass material removal rate or volumetric MRR. Was it mentioned in the problem? Not mentioned in the problem. So what was mentioned here? It was clearly mentioned that the material removal rate you calculate, in bracket it was mentioned the unit, and based on the unit I understood that I have to calculate mass material removal rate. And anyway the density of the material is not given, so there is no worry at all at this particular point. Is it true? Yes. Now the remaining numericals we can't solve. We have to go and understand the rest of the fundamentals also. Without fundamentals, this entire chapter is incomplete. Right, fine. So everybody is understanding this. Right, fine. Now let's take one example. Right, fine. Assume that I am selecting tool and this is the workpiece. Now assume that there is a gap maintained between tool and the workpiece. Now in the previous session we discussed that this is my tool, this is my workpiece, and they are being separated from each other by certain gap, by certain distance. And that gap is filled by conducting electrolytic solution. Now in the same manner, I am selecting one rod. Now the rod can be of any cross section. Cylindrical rod can be, it can be how square cross section, hexagonal cross section, triangular cross section, or any cross section. That means whatever the tool I am selecting, it must be having certain cross section. If I say that it is a cylindrical rod of diameter D, it might be having the cross section pi by 4 into d square and so on. So here this is what exactly can be a rod which is having this cross section. So this is the rod which is placed like that, and this is my workpiece surface, right? Fine. And between that rod and this workpiece, that is what called as tool and the workpiece, there is a gap maintained, and that gap is nothing but called as a inter-electrode gap. So what is this gap is? This gap is called as, understand the dynamics of this particular system. This gap is nothing but called as a inter-electrode gap, and it is seriously called as IEG, and IEG stands for what? Inter-electrode gap. Now this sometimes is also taken as L gap. So this, there is certain distance, there is a gap. Gap is measured in unit what? Millimeter. It can be 10 millimeter, 100 millimeter, depending upon the requirement. So that inter-electrode gap is mentioned by L gap. L gap stands for inter-electrode gap. It is generally measured in millimeter, which is nothing but how much is the gap maintained between my tool and the workpiece surface. Now assume that my tool has circular cross section. And when the potential is applied, assume that this entire mechanism is immersed in a conducting electrolytic solution. And the mechanism and whatever the chemical reaction that we discussed, that will keep on happening as it is. Now can I say that as the tool and the workpiece is kept at certain distance, whenever the potential is created, this tool, that whatever the tool is, it will start creating electromotive force onto the surface of workpiece. But can I say that it will create the electromotive force on only surface of the workpiece which is near to this tool surface, and whatever the surface which is far away may not be there, there won't be any electromotive force, and material removal rate will not take place from there, or material removal will not take place from there. So whichever the surface of the workpiece which is below the cross section of the tool, only that much surface of material will experience the electromotive force, and only that portion of material will start deflating the ions. So how exactly it can be understood? So I would say that literally whatever the line I'm drawing, now whichever the area is there, this area, this is the only area which is near to the tool material, which is below to the cross section of the tool, and only from that material my ions will start depleting. So can I say that roughly this is the portion from where ions will start depleting, ions will start depleting, ions will start depleting, and there might be chances that a little bit of portion surrounding to the area might also start depleting ions. That means from here also certain ions may get depleted, but not much. Therefore, can I say that from that surface of the workpiece, the ions will start depleting. And when the ions are depleting, that means can I say that material removal rate or material has removed. If the material has removed, can I say that depth of the hole will start increasing? Because from the surface, if ions are depleting, that means material is removing. That means there will be a certain depression will start creating. And whatever the cross section of the depression would be, what would be the cross section of the depression? So it's very simple that whatever the cross section of the tool is, only that much cross section of the material from the workpiece will start depleting ion. That means whichever the depression or hole will get created into the workpiece will have same cross section as the cross section of tool. If the tool has circular cross section, only through that circular cross section material workpiece will start depleting ions. If my tool is of triangular cross section, only from that triangular cross section ions will get depleted, which means that whatever the cross section of the tool I am selecting, same cross section of the hole will get created here. So therefore, we can easily understand by depleting ions, for understanding point of view, can I say that ions will get depleted, and there might be chances that up to certain depth, can I say that this material, whatever the material I am mentioning here, this material might have depleted the ions. This material might have removed in the form of ions. So can I say that depth of the hole must have increased? The moment, listen carefully, the moment depth of the hole increases because of depletement of the ions, can I say the distance between tool and the workpiece will keep on increasing? Because initially this was the distance between tool and the workpiece. Now the distance increases, and now my new distance between tool and the workpiece will be like that. So this is exactly equal to my new distance, that is new inter-electrode gap. I'll say that IEG, inter-electrode gap, that is nothing but I'll say that new. So we can use any letter. So we can say that inter-electrode gap 1. This is my new inter-electrode gap, which is greater than previous one. So when the gap between tool and the workpiece is increasing, can I say that electromotive force will reduce? If the electromotive force is reducing, can I say rate of depletement of the ions, rate of dissolution of ions will reduce, which means that my material removal rate will fall. Material removal rate will reduce. But sir, for maintaining the time required for machining operation to be as minimal as possible, because in universe, will you expect that time required for machining will keep on increasing? No sir, I expect that every manufacturing process, every machining process should perform in a minimum time. So which means that I have to maintain the optimum material removal rate. So we are not expecting that material removal rate should fall. It should maintain. And to maintain the same material removal rate, can I say that the gap between tool and the workpiece should also maintain optimum? If the gap between tool and the workpiece should remain optimum, can I say that then only there will be a material removal rate remain same? And to maintain the same optimum gap, can I say either my workpiece has to lift up or either my tool has to move in downward direction? Then only there is a gap that will be maintained optimum, because as the material removal takes place, the depth of the hole will keep on increasing, the gap between tool and the workpiece will increase. Therefore, if you observe that the workpiece size is greater and the bigger and the bulky, so the lifting of the workpiece become difficult. So instead of that, the tool is feed into downward direction. So therefore, can I say that this whatever the tool is, it will be feeded into downward direction, and therefore I'll say that sir, my tool is feeded slowly and gradually in a downward direction, and that would be done with the help of a servo mechanism. That is done with the help of what? A servo mechanism. So I'll say that servo mechanism is the one which is utilized to just feed the tool in a downward direction to maintain the same optimum gap between tool and the workpiece. So now what will happen? My tool will keep moving in a downward direction. And as the tool keeps moving in the downward direction, can I say that one point will come, it might get inserted into that workpiece also, and there might be chances that the deeper holes can be created. Deeper holes can be created when the tool is feeded into downward direction continuously. And whatever the velocity by which my tool is feeded into downward direction, that is called as a feed velocity represented by V up. And multiple questions asked on this particular platform. You must have understood that in a previous GATE question, at least 3 to 4 questions were there to calculate a feed rate in a electrochemical machining operation. It is called as what? A feed rate. Feed rate. Is it okay? Yes. Now I'll ask question, a very simple question. Tell me that when the material removal rate is higher, how much will be a feed rate? And if the material removal rate is less, how much will be a feed rate? What I'm asking, sir, feed rate means what? My tool has to feed into downward direction so that the gap between tool and the workpiece will maintain same and the material removal rate will maintain same. So if material removal rate is very high, that means rapidly ions are depleting and rapidly depth of the hole is increasing. So if the rapidly depth of the hole is increasing, the gap between tool and the workpiece is increasing rapidly. So can I say that rapidly my tool should also move in the downward direction to maintain the same optimum gap? Which means that if the material removal rate is higher, rate of ion dissolution is higher, which means that the depth of the hole increases rapidly, and therefore in the same rapid speed, my tool should move in the downward direction to maintain the optimum gap. And therefore my feed velocity should be also higher. My feed velocity should be also higher. So it's very simple that my feed velocity is directly proportional to material removal rate. $1 million statement I'm talking, and this is the year where this question might come in the examination. V up is directly proportional to material removal rate. Kitna simple statement hai dekho, right? V up is what? V up, feed velocity of what? Tool. Which is feeding? Tool is feeded. In which direction? Downward direction. And that's why we talk about feed rate is always related to tool, which is controlled by servo mechanism, which is directly proportional to MRR. In a contradictory to that, if I select my material removal rate is less, which means that rate of depletement or dissolution of ion is less. That means the depth of the hole created, but very slowly it moves in the downward direction. So if slowly moves that, in the same manner, the tool also get feeded into slow direction. Very slowly it will move in downward direction to maintain the optimum gap. That means feed velocity has to be less. That means material removal rate increases, feed velocity increases. Material removal rate decreases, feed velocity has to be decreased. Is it understood? Yes. So two statements I'll speak here. One, whatever the cross section of the tool I'm selecting, the same cross section of the hole is created. If the tool is triangle, hole will be having same triangular cross section and so on. Second, when the material removal takes place, the gap between tool and workpiece increases. To maintain the optimum gap, my tool has to feed in a downward direction with certain velocity. And whatever velocity by which my tool is feeded into downward direction, that velocity is called as feed velocity. And that velocity solely depends upon my material removal rate. If my material removal rate is very high, then my feed velocity also should be very high. If material removal rate is less, my feed velocity also should be less. As simple as that. Right? Understood everybody? Yes. Now, understand the different dynamics here of this particular process. Assume that whatever the gap is present, that is inter-electrode gap, can I say that my current has to flow through that gap? And what is filled into this gap? What is there in this that gap? Is gap ke beech mein kya hai bhaiya? So we know that, sir, in that gap, there is a conducting electrolytic solution is there. The conducting electrolytic solution, we have discussed that NaCl. NaCl stands for what? Sodium chloride. Salt water is a good conductor of electricity. So now we know that through the every medium, my current is flowing, but there would be a certain resistance created to flow of the current. So whenever my current is flowing through that gap, there must stop being certain resistance created to flow of the electrical current. And whatever the resistance created to flow the current through the gap between tool and the workpiece, through that inter-electrode gap, that resistance is nothing but represented as R. That is called as what? R. So I'll say that here, R is nothing but inter-electrode resistance. Inter-electrode resistance. And resistance is always measured in the unit what? Ohm. Ohm is the unit which is used to measure the resistance. Is it true? Yes. And now can I say, suppose whatever tool I'm selecting, suppose assume that tool is a cylindrical and which is having certain diameter. Cylindrical body hai to diameter hoga. Is it accepted everybody? Yes. If the cylindrical body hai, it has a certain diameter, which means that it might be having certain cross section area. So if I say that, for example, that cylindrical tool which has a diameter d, so what is the cross section area? So cross section area will be exactly equal to pi by 4 into d square. Pi by 4 into d square. This is what cross-section area. So can I say whatever the cross-section area is there, through the entire cross-section area, my current will flow through that open medium or that conducting electrolyte solution and will travel towards the workpiece material. And whenever throughout that area, through that interelectrode gap, when the current is flowing, it will resist, or that current will feel resistance. So I'll say that A is nothing but called as a cross-sectional area of tool. Cross-sectional area of what? Tool. Cross-section area of tool. Or can I say that whatever the cross-section area of the tool is, the same area of the workpiece from where material removal takes place? Might be a little bit of extra, but if I neglect that, so cross-section area of the tool and the cross-section area of the workpiece from where material removal takes place, both are same. So can I say that A can be called as a cross-section of the dimension of the workpiece which is getting machined? A is nothing but called as what? Either cross-section of the tool or same cross-section from where the workpiece removal material or material removal takes place, which means that A can be considered as the area of a machine surface. Area of a what? Machine surface. Or it can be considered as area of my tool. Area of my tool. So I understand R and A. Now can I say whenever these two conducting electrolyte are connected to power supply, that means there must have been certain potential applied. So whatever the potential is applied, it is nothing but called as VA, stands for applied potential, applied voltage, applied potential, right? Or it can be also called as VS, nothing but called as a supplied voltage or applied voltage. Any statement can become in GATE examination. So applied voltage and supplied voltage, both are same, applied, right? Voltage is applied. VS, supplied voltage, right? Whatever that power supply is given, based on that there is a potential created, and that whatever potential is applied, that is called as applied or supplied. Both are same, and both statement already used in a GATE examination. When we solve now numerical, you will understand that. So we understand VA, that is applied voltage, and VS, that is supplied voltage, right? Fine. Now I'll say that, sir, I is exactly equal to current which is flowing through the circuit. I is exactly equal to what? Current which is flowing through the circuit. Is it understood? Yes. So again I'll repeat myself. Sir, A is the cross section area of the tool, or A can be cross section area of the machine surface. Both are same. Now R is nothing but the resistance created to the flow of current between the interelectrode gap, and that current is flowing through that entire area of the tool or workpiece material. Now whatever gap is maintained between interelectrode, that is called as L gap. It is a distance measured in millimeter. And VA and VS are called as applied voltage or supplied voltage. Is it understood the dynamics of this particular? Okay, understood. Very happy. Yes. Okay. Okay, fine. Now क्या लगता है आपको कि when the question comes in GATE examination, is it like that simple terminology and simple statements will be given, calculate material removal rate? That means we have understood that, sir, MRR, that is mass material removal rate, that is what? Mass material removal rate is exactly equal to A into I divided by Z into F. A into I divided by Z into F. So do you think that the examiners are that much, particularly I would say that board, that they'll give A value, that is gram atomic weight, and the current and the valency and Faraday's constant, and ask the students calculate MRR gram per second? No. So instead of giving the current, listen carefully, and here the number of question comes. What is that? Instead of giving the current, rest of the values are deliberately given. So what is given? Instead of giving the current, applied or supplied voltage is given. That is what? Applied voltage or supplied voltage is given. Is what? Given. And what is the resistance? Resistance created to the flow of current between interelectrode gap. Where is that? Where is it? Where is it, bhaiya? Kahan pe? Yahan pe. When that whatever the current is flowing through that cross section area between interelectrode gap, that current will feel the resistance. In what? Ohm. So instead of that particular current, what values are given? Generally, the applied or supplied voltage are given, or a resistance is given. Resistance is what? Given. And then you are asked to calculate mass MRR. Now, sir, don't worry. We can able to still solve the problem, because there is a relation between voltage, current and resistance. There is a standard relation which is in the blood. Since the childhood we understand that, sir, V is exactly equal to what? IR. V is equal to potential difference is equal to current into resistance R. So suppose then the potential is given to you, or applied voltage or supplied voltage is given to you, and resistance is given to you, nothing to worry. Current can be calculated from here directly. So we can say I is exactly equal to voltage divided by resistance. This is applied voltage or supplied voltage. You tell me that. Can you able to do this particular simple story? Yes, sir. Simple story, I do it. Right? So I'll say that, sir, this would be exactly equal to my answer. Okay, if the current is not given, if applied or supplied voltage is given and resistance is given, we can use that to calculate current. Any problem in this? Yes. So if it is given, I'll directly calculate current, that is applied or supplied voltage divided by resistance. Now one more problem is coming over here, and we'll go in a further direction. Furthermore direction hum jayenge, and you understand that instead of giving the resistance, one more term is coming. It is nothing but called as a resistivity. Resistivity. I'll say that rho resistivity. One more term is coming. Fine. And one more term is coming, a over potential voltage, VO. Very important from gate point of view. Over potential voltage. Over potential voltage. Now the $1,000,000 question is that what is over potential voltage? Now over potential voltage is nothing but over and above the potential which is not used in the system, that is called as over potential. Let's understand that. Let's understand from the definition. It is directly given. The over potential is the additional potential beyond the thermodynamic requirement needed to drive an electrochemical reaction at a certain rate is called as over potential. Now simple term is what? Suppose I'm taking one example. How exactly we should decode that? Suppose it is given that the applied voltage or supplied voltage is exactly equal to 100 volt. What is applied voltage? Applied is 100 volt. But a thermodynamic requirement of this is called as actual voltage. Thermodynamic requirement is what? Actually how much is used in the system. So I am applying sub 100 voltage, but there is out of that 100 voltage, there is a some voltage can be over potential which is never used in the system. And whichever the voltage that is actually utilized, which is called as actual voltage which is used in the system, and that over potential voltage, if it is given, is exactly equal to 5 volt. So what does it mean by that? It means a simple statement that, so whatever applied voltage is 100 voltage. Out of that, over potential voltage is 5 voltage, which is beyond my thermodynamic requirement. It is the additional potential which is not required to drive electrochemical reaction, right? And therefore which is never used in the system. If it is never used in the system, it should not be used during the calculation of mathematical material removal. And therefore I'll say that, sir, my actual voltage is exactly equal to 100 minus 5. So only 95 volt is used in the system. So why you use 100 volt? Because out of 100 volt, 5 voltage is over potential. It is beyond my thermodynamic requirement, and therefore I'll say that actual voltage used in the system is a supplied voltage minus over potential voltage. The supplied voltage minus what? Over potential voltage. And therefore we can say that, sir, there is a terminology is coming, over potential, and this question was asked in GATE examination. So if the over potential is given to you, then my current value is coming, I is exactly equal to a applied voltage, applied or supplied, minus over potential divided by resistance R, divided by resistance R. Is it understood, everybody? Yes. Slowly student will come and join us. Slowly they'll understand the dynamics, right? So we'll be going to the rock start steady station or steady stations. Don't worry about it, right? Slowly students will realize that how beautifully these concepts are going on, and we'll coming up with the next series with the numerical or concepts through numericals, PYQs, and only numerical point of view discussion will be having in the next week or so on. So if applied voltage and over potential is given, you have to subtract that from applied voltage. Clear hai sabko? Bhaiya Vishnu ji? Everybody clear hai sab what exactly I'm speaking about? Yes. And now next statement. So now ek aur yahan pe the thing is coming. So instead of giving resistance, there is a coming called a specific resistivity. That is called as rho. Rho stands for a specific resistivity. Resistance is not given generally. Specific resistivity is given. Specific what? Resistivity is given. Just a minute. I'll connect charger. One sec. Okay, fine. Am I audible, everybody? Yes, I guess. Right, fine. So now we'll talk about specific resistivity. Now, what is specific resistivity? Specific resistivity stands for resistance created to the flow of current per unit area, per unit length, per unit length, per unit area. Is it true? Yes. So what is meant by that? This is the gap. And that gap is nothing but interelectrode gap. And that gap is mentioned with the letter L gap. Already we talk about. It can be called as interelectrode gap or it can be called as L gap. It is called as interelectrode gap. Is it true? Interelectrode gap. Now through that gap current is flowing. And when the current is flowing, there is a certain resistance created. Simultaneously, that current is flowing through that area. Suppose I have this particular tool which has certain cross-section area. Through that cross-section area, current is flowing. And when the current is flowing through that, can I say that this entire area will also resist the flow of current? And through that, there is a one definition is coming called as specific resistivity. The specific resistivity is nothing but resistance created to the flow of current per unit area, per unit length. And definition of resistivity is it is not a density, it is a resistivity is exactly equal to resistance created to flow of current per unit area. Area, kiska area bhaiya? Area of the tool or area of the surface which is going to get machined, because both areas are same, divided by interelectrode gap, L gap. What is the unit? Resistance is mentioned in the ohm. Area is mentioned in what? Millimeter square. And the interelectrode gap is mentioned in what? Millimeter. So unit will be what? Ohm into millimeter. Ohm into millimeter. It is called a specific resistivity. So specific resistivity is given to you. Resistance is not given. Allah, don't worry. Sir, if the specific resistivity is given, resistance is not given, we require a resistance to calculate a current. Now journey, let's see that. But area might have given, interelectrode gap might have given. So from that, can I able to calculate R? So from that, I'll simply say that, sir, R is exactly equal to, that is resistance, is exactly equal to resistivity. Don't get confused. Rho is not a density here. Rho is a resistivity multiplied by L gap, interelectrode gap, divided by what? Divided by area. Divided by what? area. It is not a current. It is not gram atomic weight. A stands for area and that's why suffix is given area, area, area. Rho is not density, it is a resistivity. Is it true? Let's see now beautifully. Sir, resistance is not given. What is given? Resistivity. Don't worry. Use resistivity. Multiply by interelectrode gap divided by area. Calculate resistance. Once you calculate resistance, come back here. From that resistance, calculate current. Once you calculate current, you calculate mass material removal rate. And one more drama these people are doing. And the drama is nothing but instead of resistivity, one more term is coming which is called as a sigma conductivity. It is called as what? Sigma conductivity. Conductivity sigma. That is what exactly. What is sigma conductivity? Sigma conductivity is exactly equal to 1 by rho resistivity. Resistivity is it was exactly. So instead of giving the resistivity, they are giving sigma conductivity. So again it becomes very simple, sir. Let it give that sigma conductivity. So can I say that I'll use and calculate from here, or I'll say that rho resistivity is exactly equal to 1 by sigma conductivity. 1 by sigma conductivity. Is it accepted, everybody? Yes. Kicking and alive? Yes. So I'll say that this is sigma conductivity. Conductivity. Now let's say that, sir, how many formulas are there? And through that only peanuts of formulas, every numerical which comes in a GATE examination on the ECM, you can be able to calculate, but we are just not paying enough attention. And everybody is getting all India rank 1. Is it true? Yes. So let's see that now. What is it? Conductivity is given. Take 1 by sigma conductivity. Calculate resistivity. Once you calculate resistivity, from that resistivity calculate resistance. Once you calculate resistance, from that resistance calculate current. Once you calculate current, you put it here and calculate material removal rate. And once you calculate material removal rate, you will get all India rank 1 directly. We are banking on all India rank 1 and we are talking about all India rank 1. There is no rank is accepted over here below that, right? Or above that. Only we are just banking on 1 rank. Below 100. Is it true? Yes. Is there any doubt here? No. Understood everybody? Yes. और एक केस है और एक गेम है, and that is what exactly beautiful question was asked in 6 times in or 5 times in GATE examination. Let's see that. देखो अब बोलो, अब क्या बोल रहा हूँ. Sir, VF is feed velocity. What is feed velocity? बोलो भैया, what is feed velocity? Vishnu, Sumit, everybody who is there, right? Sir, you just style Telegram group, right? Telegram group is coming very shortly. I joined newly, so I don't know much of etiquette. So I haven't reached to the maximum people, but in very short time I'll reach to the people. I'll talk to the people. We'll interact and we'll have beautiful sessions. Very soon you'll see that one game changing. Time is changing. Time is changing. BYJU'S exam prep is coming with the master faculties and the master content. Believe me that, and that is going to happen. भैया मौसम चेंज हो रहा है, मौसम चेंज हो रहा है. देखो प्यार से देखो, होम टू फॉलो, बिकॉज भगवान जो होते हैं ना बड़े प्यार से चुनना होता है, राइट. आई होप सो विल ऑल मीट वेरी सून and we'll have a wonderful blasting sessions. Just wait. The time is changing, world is changing, BYJU'S exam prep is changing. We are all banking on only what? Quality. Quality is the only ultimate parameter that we are banking on. Right, fine. अब एक क्वेश्चन का आंसर दे दो मुझे. ये में सपोज फीड वेलोसिटी इज गिवन. नाउ यू आस्क मी सर व्हाट द हेल इज फीड वेलोसिटी. अरे भैया अभी देखा ना, फीड वेलोसिटी क्या है? द वेलोसिटी ऑफ द टूल बाय व्हिच इट इज फीडेड इनटू डाउनवर्ड डायरेक्शन टू मेंटेन ऑप्टिमम गैप. सपोज मान लो फीड वेलोसिटी इज गिवन टू यू. लिसन केयर, फीड वेलोसिटी इज गिवन टू यू and area of the tool is given. What is given? Area. Area of tool is given. Or I'll say that feed velocity is given. Feed velocity is given and area of a tool is given, or machining surface, whichever surface which is going to get machined, that is machining surface area is given to you. These are the two values are given to you, and from these two values I am asking you what is MRR. What is what? MRR. So what else is coming? Yeah, I'll tell you that what else is coming. I'll tell you a very simple story that whatever the entire production and industrial is there, I'm going to cover it with unmatched level, unmatched content. Tomorrow we have HPCL mock test, right? Please join me and let's see that I'm going to solve certain 10-15 questions from production and 5-7 or 10 questions from industrial engineering. Please come and do join and just take a feel of quality what exactly we are going to deliver. Just come and just see that and what exactly is coming up, right? Fine. Tell your students, tell your friends and everybody, this is going to be one of the best sessions of your life. I bet you that once you attend, you will never regret. You'll never regret my sessions. This is my challenge. I'm not talking about anything. I'm just talking that I'm giving a solid fundamental content. Okay, no wastage of time. Tell me metal remove rate. Metal remove rate बताओ भैया. सुमित बताओ, विष्णु बताओ, rocket science or rocket fire बताओ. Yes, tell me that. What is metal removal rate? Calculate कर सकते हैं यहाँ पे metal removal rate. It's very simple that sir. Metal removal rate. What is formula of metal removal rate? Metal removal rate will be mm cube per second, right? So can I say that from here my material removal rate is exactly equal to metal removal rate. Material removal rate. Waiting for the other Avengers? You'll wait very soon. One Avenger is coming your way, and then we'll have a lot of juggle. Don't worry, Sumit. Very soon we'll see that Avengers team is coming. An Avenger team is here to blast. Don't worry. Very soon you'll see that. अरे मटेरियल रिमूवल रेट बताओ भैया, ये तो होता रहेगा. एवेंजर्स आएंगे या तो जाएंगे. गेट एग्जामिनेशन का सक्सेस इज इंपॉर्टेंट फॉर अस. टेल मी दैट व्हाट इज एमआरआर. देखो भैया, कैन आई से दैट एरिया ऑफ द टूल एंड एरिया ऑफ द वर्क पीस इज द सेम. And this is the area from where material is removing, and what is the velocity by which tool is feeding? Can I say same is the velocity by which material removal takes place? Same is the velocity. So can I say my material removal rate will be exactly equal to cross section area multiplied by what? Feed velocity. Cross section area multiplied by feed velocity. क्या है feed velocity? mm per second. क्या है एरिया? मिलीमीटर स्क्वायर. व्हाट इज फॉर्मूला? यूनिट mm क्यूब पर सेकेंड. mm क्यूब पर सेकेंड इज नथिंग बट व्हाट? वॉल्यूमेट्रिक. इट इज नथिंग बट व्हाट? वॉल्यूमेट्रिक एमआरआर. वॉल्यूमेट्रिक एमआरआर भैया, वॉल्यूमेट्रिक एमआरआर. इज इट अंडरस्टूड? देखो प्यार से, दिस इज माई टूल इज हैविंग क्रॉस सेक्शन, इट इज मूविंग इन द डाउनवर्ड डायरेक्शन. ये कब नीचे जाएगा? When the surface of the workpiece ka material, when it is removing, then only it will move in downward direction. So what is the velocity by which it is moving in a downward direction? Same is the velocity from where the surface materials are deflating. So क्या होगा मेरा MRR? Surface area multiplied by downward velocity of the tool, and that is nothing but VF multiplied by area is nothing but what? Volumetric MRR. अब भैया, if I ask you, calculate the feed velocity, and that's what simple question was asking, and everybody is crying there. क्या ये? This is a simple task. Every day we do that. Can I say that from here? Feed velocity is exactly equal to what? MRR divided by area. Which area? Area of the tool. Area of the surface which is getting machined. So can I say that from here? From here, feed velocity VF is exactly equal to MRR. But not only MRR. Which MRR? Volumetric MRR. So I'll say that volumetric MRR. Volumetric MRR divided by what? Divided by what? Area divided by what? Area. Is it true, everybody? Volume of material removed per second. I'll say that VF volumetric MRR divided by area. And कौन सा area है भैया? Area of the tool or machine surface. So here can I write down the feed velocity can be calculated by the formula volumetric MRR. जरा बताओ तो volumetric MRR का formula A into I divided by rho density into what? Z into what? F divided by area. Don't get confused between the definitions. Here A stands for, A क्या है भैया? बताओ दिल खोल के. What is A? A is what? Gram atomic weight. What is I? Current in ampere. What is rho? Density. Density should be in what? Density should be in what? Density should be in what? I told you that. Density is nothing but mass divided by volume. Gram per mm cube. Gram per mm cube is what? Density. Z is nothing but, sir, valency. No unit. Right? F, Faraday's constant. A, area. Mm square. And the answer will come feed velocity mm per second. अगर per minute में चाहिए तो multiply by 60. Multiply by 60. Is it true? VF is coming mm per minute. Mm per minute. अरे भैया, mm per second आएगा ना? It's a velocity. Velocity. We have to move very fast in our life. Velocity. Is it okay, everybody? What is the unit of density? Density has to be in gram per mm cube. Density has to be gram per mm cube. Kg per meter cube should not be accepted. Kg per meter cube should not be accepted. And चलो देखते हैं क्या न्यूमेरिकल दिया है इसने, राइट? गेट एग्जामिनेशन में हमरे आगे क्या चिंग करता है. चलो, गेट एग्जामिनेशन PI question was asked, and it was asked 2017. Solve the numerical. Tell me the answer. Beautiful session is there in front of you. अरे बच्चे भी आएंगे, सब होंगे. दुनिया बदल रही है, हम बदल रही है, आप भी बदल जाओगे. इल्ली टिल्ली उनको हटाओ. Come on. Yes. BYJU'S exam frame is coming with a new talented, I would say that. What is that? New energetic people. बोलो भैया, आंसर बताओ. A surface of 30 by 30 mm of an iron block is machined. ये 30 by 30 क्या है? It is the area which is getting machined, which is nothing but exactly equal to cross section area of the tool. A surface of 30 by 30 mm of iron block is machined using electrochemical machining process. The atomic weight and the valency of iron is 55.85 and 2 respectively. The density of iron is 7860 kg per meter cube. Why हुआ? Kg per meter cube. I don't require. I require what? Gram per mm cube. Okay. If input current is 1000 ampere and the Faraday's constant is 96,540 coulombs, then the feed rate in mm per minute. Feed rate in mm per minute. That was the question that I was talking about. Solve the question and tell me that answer. So I'll write down the formula, or I'll write down the data. Area. How much is the area? 30 by 30 is area. 30 by 30 is the area. Right, fine. The atomic weight, gram atomic weight, A weight, gram atomic weight is exactly equal to 55.85 gram atomic weight. Valency Z, how much it is? 2, right? The density of an iron, density rho क्या है भैया? Density is how much? 7860. But ये क्या है? Kg per meter cube. What do I require? I required it has to be there in what? In terms of gram per mm cube. Gram. How many grams? 1000. That is 10 to the power of 3. राइट फाइन, डिवाइडेड बाय mm क्यूब टू द मीटर क्यूब, क्यूब को कन्वर्ट करना है क्या, सॉरी ये केजी पर मीटर क्यूब है ऑलरेडी, this is what kg per meter cube. I want to convert into what, cube. 1000 is equal to 1 meter, so 1000, that is 10 to the power of 3 to the power of what, 3. So therefore it will be 10 to the power of 3 divided by 10 to the power of 9. If I come to the numerator, it will be 7860 into 10 to the power of minus 6. And what is unit, gram per cube, gram per cube. And the students who understand that, bang on all India rank 1. That's it. Now rest is what, just a cakewalk. Come on man, right? So F is what, 96,540 coulomb charge. That is what coulomb charge. Is it true? Yes. Current value I, how much it is, 1000 ampere is the current. Is there any doubt? Not a single doubt. Don't keep the doubt in the heart. When I am there, never fear. Right? Fine. Okay. What are you waiting for? Just put the value there. Sir, what is interested to calculate? VF. VF क्या है? Feed velocity. Feed velocity is exactly equal to what? Volumetric MRR divided by area. So A into I. A into what? I divided by rho density into Z into F divided by area. Answer will come what? mm per second. I record mm per minute. Multiply by 60. Don't forget to multiply by 60. Is it true? Now your chance is there, or your just task is there. Put the value into the Potter format. Put the value there in the proper format. किसी का आया क्वेश्चन का आंसर कुछ आया, कैलकुलेट कर रहा है किसने? A stands for what? Gram atomic weight. कितना है gram atomic weight? Sir, gram atomic weight is 55.85. Put it there. Yes, 55.85. Multiply by current. Multiply by current. How much it is current? 1000 ampere current. Right, fine. Rho density कितना है? 7860. Multiply by 10 to the minus power 6. Valency is 2. Faraday's constant 96,540. And the area 30 by 30. Multiply by 60 to convert mm per second into mm per minute. Mm per second into mm per minute. कितना आ रहा है आंसर? How much is answer भैया? How much you have calculated? Sir, आप ये लिख दो, आप ही करो कुछ जो कि करना है, right? No, you just style multiply by 60 भैया. It is coming 2.453 mm per minute. Mm per minute. Mm per minute. This is from the series of Avengers. कैसे आएगा रे बेबा, कैसे? 2.54, 2.45, spot on, Bhavya, spot on. Love you everybody. क्या ECM है? What is ECM? In the entire life, I'll solve these numericals in the same manner. No issues. 2.45, Bhavya, spot on. Is there any doubt in this question? ऐसे क्वेश्चन चिल्लर आते हैं गेट एग्जामिनेशन में. That's it. Shall we go to the next question now? I hope you understand the strategy. Question 17 को पूछा था. Okay, no worries. इसको तो हमने बल्ले बल्ले कर ही दिया. Now the next question is it true? Very important question. कैसा क्वेश्चन दिया है देखो. How the question is given. Let's see. चिल्लर ही है आपके सामने. During the electrochemical machining of an iron, atomic weight 56, valency 2. At a current 1000 ampere with a 90% current efficiency, the material removal rate observed was 0.26 gram per second. Data over for iron material. Right, fine. If the titanium material has an atomic weight of 48 gram and the valency 3 is machined by the ECM process at the current of 2000 ampere with again 90% current efficiency, the expected material removal rate in gram per second. Expected material removal rate in gram per second. A is atomic weight. Absolutely true. A is atomic weight, Bhavya. So A is atomic weight, we have already written there, right? 55.85. A is atomic weight. Gram atomic weight. It has to be in a gram. Gram में होना चाहिए भाई. Yes. ये क्वेश्चन बना है और बताओ मुझे क्या है सीन. ये क्वेश्चन, this is the question that we are waiting for. देखो किस प्रकार, how exactly these questions need to be get solved. Simple story, I'll tell you. Whatever the first half is given, you write down the data of the first half, which is related to the iron material. Which is related to which material? Iron material, right? So Fe material का जो है, you write down the data. You write down what data, and then you tell me that what is missing there. What is missing there? Right, fine. So I'll say that, sir, for ECM process, for Fe material, the gram atomic weight A is exactly equal to 56 gram. A stands for gram atomic weight. Valency Z is exactly equal to 2. The current I is 1000 ampere, but point to be understand with efficiency 90%. What is meant by 90% efficiency? The 90% efficiency means even I'm supplying the current to 1000 ampere, out of that only 90% of the current is used in the system. Only 90% current is used in the system. If only 90% is used, I should also use the same current during calculation. So you multiply by 0.9. So this is my current is going to use in the system, and material removal rate from here is calculated as 0.26 gram per second. Gram per second. Here can I say that gram atomic weight is given, the current is given, valence is given, material removal rate is given. What is missing? Faraday's constant is missing. Faraday's constant is missing. And in the next case, if the titanium atomic weight 48, valency 3 is machined by the ECM process at the current of 2000 ampere with a 90% current efficiency, the expected material removal rate. Here also all the data is given, and I'm interested to calculate material removal rate. So here to calculate material removal rate, what do we require? I required a Faraday's constant. What do I require? Faraday's constant. So whatever the data is given for iron material, from that data you calculate the Faraday's constant, and that same data of Faraday's constant you use it during the calculation of material removal rate of titanium material. Do you understand that? Such kind of problem has to be dealt with this like that. Is it true? Yes. So I'll tell you that. Here I'll just use this to calculate. So I'll say that the material removal rate, that is mass material removal rate, I'll say precisely mass material removal rate. Density is not given, that means mass material removal rate. It is A into I divided by Z into F. Z into what? F. Is it true? Yes. What is material removal rate? Gram material removal rate, that is 0.26 gram per second. Gram per what? Second. Exactly. A कितना है? 1000 ampere. But efficiency is what? Current efficiency is 90%. Please multiply 0.9. Don't use 1000 current. Don't use 1000 because efficiency is given. Right? Fine. And gram atomic weight. Okay, I have written current first and then gram atomic weight. I'll write down 56. No worries. Right? Understood. Z valency. Valency is given 2. And then only unknown is F. F is Faraday's constant. If you calculate that, Faraday's constant is coming 96,923.07 coulomb charge. So this is exactly equal to my Faraday's constant is coming. This is exactly equal to my Faraday's constant is coming. आ गया Faraday's constant. Faraday constant बड़ी बात है. Faraday's constant, if you calculate, use the data of titanium material and calculate it. So I'll say that, sir, mass material removal rate for titanium material, mass material removal rate for titanium material, A into I divided by Z into F. What is A gram atomic weight? 48. What is current? Current is 2000 ampere. But again 90% efficiency, 0.9 into 2000 divided by valency. Valency of titanium material is 3. And Faraday's constant, just now we calculated 96,923 roughly 0.07 coulomb charge. And you'll get the answer. Material removal rate here is coming exactly equal to 0.297, which is exactly equal to 0.3 gram per second. 0.3 gram per second. Gram per second. 0.3 gram per second. This is nothing but done and dusted story of ECM. I know that we are dealing with the production which is very theoretical, and on the YouTube session students are preferring more or less numerical. Bhavya, absolutely correct, 0.297. I love you, and UJ style also superb. But I promise you that the coming sessions would be only on numerical type. That is nothing but the concept through numericals. and we are going to unfold the beautiful concept of this manufacturing processes as well as industrial engineering. I'm damn sure about it. So this is just one introductory session I was about to take to have interaction with the students. Then we'll find and we'll start generating. I'll generate my one Telegram channel. I'll give the link to the Telegram channel on the BYJU'S platform. I'll be available. I'll interact with the students, and then we'll see a difference in the teaching. That's what exactly we are here for. Right, fine. I hope so you must have enjoyed and understood this particular session. Yeah, no doubt at all in this case. Yes. Is it true? Yes. So I'll say that, sir, whatever I have promised, one process, electrochemical machining process, in the best possible manner, we have covered. We are all thankful. I'm thankful for showing the love and asking me the next sessions, everything. All the next sessions and everything will be conveyed to you very soon on the Telegram channel of mine. Right? Fine. कोई doubt है किसी को? Is there any doubt, anyone? Right? Is there any doubt, anyone?
Sorry, could you say that again?
Vishnu, enjoy and learn new things? Absolutely, Vishnu. I'll beg you that if you come and join me for production, I will let you enter into the new world of production. Thank you, Vishnu, for this. Bhavya, any doubt, Bhavya? And UJ style, clear? Crystal clear, Vishnu. Okay, thank you. UJ style. Very nice session. Okay, UJ style. I'm very thankful. I'm very thankful for this, everybody. Right, fine. As I'm new to the system, so a number of things I don't know, but very soon I'll get to know all these particular things, right? And I'll do one thing, that what I'll reach to the students and I'll create one channel so that we can communicate to the students. We'll try and find out the way to come up with what series to come up with students, कौन सा topic लेना है, numerical should be covered, PY should be covered. So I'll take that decision, and one topic very soon I'll come across with you, that is concept through questions. Concept through questions. Meanwhile, tomorrow at 11 a.m. we'll be having HPCL mock test. In that HPCL mock test, after Dheeraj Sardana and one more faculty is there, I think so, Chandrasekhar sir. After that, I'll be joining you for production and industrial. So after Dheeraj sir and after Chandrasekhar sir, I'll be joining you. Just please do log in at that particular point. Let's see that how exactly things and the questions comes to the HPCL exam also. Right, so I hope so you must have enjoyed the session. Take care and see you very soon with the new series, a new energy, new zeal, and new faces. Right, thank you all, everybody, and thanks for the love. We'll come back with the solid sessions upcoming. Okay, so take care till then. Happy learning. Yes, bye bye.